this rack, that rack in the middle of the switch in the middle, if you are cabling those, you're gonna be, the operator has to walk around, right? The things has to be cleaned, and some carts might be moving in and out. So that's just for convenience of the cabling. It makes sense, right? So if this was not opening, I open this. I was trying to download the newer version of the. Let's just do with this. So let me hear still a few comments. Students sitting in the back. Maybe I will go through all these students. Last one. Tell me one word from last class. What's that? Data center. Okay, then the computer models. Warmer? Different types of computers. All we have one server access for multiple places. If one data center and we access to multiple places. Yeah, that's over the network, right? Is it data center
Server major components.
server convergence.
Types.
Yeah. Oh, different server, different server types. What kind of server types? Cloud server, web server. Web server is the one. IBM IBM Enterprise, the G Enterprise, so those are the enterprise mainframe, right? So it's not just PC, it's not just server. We still have a mainframe that we used to have made. In my other class, I have someone from who's a senior in the industry who has an experience of all the older version of the systems. He was delighted to see IBM mainframe. Okay, so can I, excuse me, you were in before we did this, right?
Yeah.
Yeah, you were in
Lobby.
Lobby.
Yeah.
Is this your first time?
I don't know. I did not came to school last week because our tab, yeah, I just come back next week.
Okay.
Yeah, not last week, not Tuesday. Actually.
Okay.
Yeah.
You know what? UMKC Connect, that they say, student doesn't attend the first week class,
I was here in first week. I was here in first week.
Okay.
Yeah, last Tuesday.
Alright, yes. Just check the slide quickly and tell me one word about last week. In the meantime, I will ask you. Computing model. So this is open book, open. You can take a look, right? This time you're trying to say something different. Data center hardware. Okay, good. That's a big stuff. You want to add?
Data center connections and how collaborative.
Data center connection. Front end and so these are the things that I want to actually profile. It doesn't. When I ask the question, this question doesn't mean that what's the key idea summary. It's just what the student might remember, like some cabling issue from the cable, right? So what seems to be interesting to students. I want to learn, so that's why I'm asking question. Anyone want to ask?
CPU versus core.
Oh, right. Yeah, that's the last one that we were left off, right?
Yes.
Thank you. So core shares the L3 cache, right? The which slide is it? So even within a computer, the trend has been rather than one big powerful, because as you will see later, Moore's law is slowing down the computer, the the circuit density is not getting really higher in a fast rate, doubling every 2 years. That's not really happening. But still, we want to do better and better. And other strategies, making it using multiple. And already within the system, we've been using multi-CPU, which is expensive, multi-core. It can actually achieve pretty good performance without having too much resource. When we say the processor, it includes typically computing unit, but there are for us, when we say someone's smart, it's for us to think well, we do need memory, short-term memory, and the long-term memory is an extra thing. But short-term memory is really important for the quick thinking, right? And there are short-term memory SRAM, and there is a L1, L2, L3, different layered hierarchy of the caches. And if we use a shared pool of those SRAM, the memory among the small CPU, meaning cores, then we can achieve pretty good performance without having separate, the all the cache memories. So that's the idea. So really, history or looking at the bigger spectrum helps you think that what the future trends will be like. Already within the system, we've been using multi-cores rather than, big CPU. Of course, we want to make it bigger and bigger, but it's not getting faster. Faster at the rate we used to see before. So here is processors. Here we have in this picture there are 4 processors. Processor will have multiple cores, and this is shared. You don't have to see I know it's not so visible, but here the main point is that when we say processor and core, there are some differences, and know what is the differences about, and why we use multi-core. Why not just use multi-processors? And there is a cost reason. Having a good architecture help us to achieve a good performance without using too much the resource cost. So yeah, that's the point. I don't expect you to memorize these ones. The number keeps changing, but again, hierarchy, shorter, smaller, faster. Question. Yes.
What is an ALU inside the core?
What's it?
ALU, that's what's in there.
ALU, arithmetic logical unit. That's a part of the CPU. Yeah. So this is the kind of picture you will see in computer architecture course. Yeah. So for any the core to think, there should be this is really the core of the thinking, arithmetic, computation, and the logical, and or this kind of computation, and this is the controlled when to do add, when to do or things like that, and it does require some short-term memory. That's what it meant. We talked about these different racks, KVM switch, hierarchy. Oh, so we didn't talk about this in this class yet? Okay, so storage device, SSD is the major the device these days you use probably in your laptop, it has storage is actually an area that is evolving very fast, more faster than CPU. So the up until very recently, we used to have HDD as a main option in your server computer when you try to purchase it. And the just here, these are the names for HDD, bus protocols, and these all acronyms. I guess you have heard of those, right? At least you know these are the protocols, standards that has a syntax, semantics, and the order of messages to be able to send and receive, transmit data.
So we know the everything is becoming the SSD type, but
No, so actually the point is, what I'm saying that SSD might be the one that you experience the most these days, but the future ones also coming. The cloud data centers, HDD, and even optical ones are being used. Okay, so don't think that one type.
that's my question. Still, we use the HSD in big data centers.
Yeah.
Okay.
Absolutely. DigitalOcean is the one, the first cloud provider. They say we use everything SSD. That's a big kind of commercial,
Yes.
propaganda. But still, they all kinds of. So here, point is that storage typically we have a diverse type of storages, and there are some characteristics as we go higher in the pyramid. CPU register, cache memory, main memory, DRAM. So these are SRAM. This is a DRAM. This is really fast. However, it's expensive. Higher in the cost. So you cannot have everything, the data stored over here. Particularly, there's a line over here, above volatile, below non-volatile. DRAM, SRAM, RAMs are the volatile. Right? Storage, SSD, HDD, these are non-volatile. So you might. How about your memory? Is it volatile or non-volatile? Right? I feel sometimes volatile. I was learning something recently. After the test, I find that I completely forgot all the previous one. Anyway, we use this joke a lot in computer science, especially among students. I think. So even in each the category, volatile or non-volatile, we still have a multiple diverse types of storage. And always in the operating system course, this picture is from OS textbook. So operating system class, they always say this is a storage pyramid. The point is that there are different technologies, diverse technologies are being used, and there are trades-off, expensive, less expensive, right? The faster, slower, right? Capacity is small, therefore, because it's expensive, it's small, and it is can be large. So you have to have a right strategy. Do I put this data in SSD or HDD? You have to have a right strategy for your purpose. Okay, so even UMKC, we'll say that again and talk about it again. The AWS, they have a lot of different type of storage service, not just the object storage, file storage, block storage. Even they have the service product called like a glacier, something very cold. That means it's okay. The performance it's not that important. Performance, it's less of an issue. However, it needs to be stored, right, for backup purpose and so on. So in such a case, you think where in the pyramid, what kind of storage technology they're gonna use? Higher in the pyramid or lower in the pyramid? The one that is less accessed.
Lower.
lower, right? Yeah. So that's exactly the point, right? So I didn't give you a chance to ask a question. What's that? Lobby, right? Yeah, lobby. Yeah. So feel free to I want you to have a chance to speak in the class. This is a HDD. We are software. Well, at least this class. The students here are really software, people. You're gonna be software engineer or you're gonna do something about software. However, operating system, cloud computing, and networking, these are so-called the systems area. We focus on software. However, uh, we are right above the hardware, and knowing the hardware is really important to better utilize the hardware, right? So I give it like there are a lot of examples in the networking class. I say the good example is that if the protocol is a so-called stop and wait, no matter how high bandwidth the link might be, if the protocol itself, you send one packet and then you have to wait until the acknowledge comes back and you cannot send in between, then your utilization will be really, really low, especially over longer distance the link, right? So, in such a case, what you want to do is improving the protocol, making it a pipeline protocol rather than the, upgrading your hardware, expensive hardware resources. So that's important. We have a number of examples, and that's what I want you to have. What you have as an insight. So HDD, this is a picture, and this is a more the systematic diagram, or this is a picture over here that is easier for us to take a look. There is a cylinder that keeps rotating, and there is a read-write head that goes in and out. So when data is written on certain disk on a certain the sector, the read-write head was right above it. Right? So if you think about this kind of architecture, this is a mechanical, electronical, but also mechanical device. There, you cannot beat, as a software people, you cannot make the hardware run faster. RPM, rotation per minute, that's some performance measure of the hardware HDD. But still, there are things that software people can make the performance better, and that is disk scheduling. So here's the different diagram. See, there is a read-write head. This platter, multiple platters, and read-write heads for each. There is a sector and a cylinder, and data will be written over here. This read-write head, first of all, go into that cylinder, and sector has to rotate. So there is a mechanical part in there. How can we do better? Part of the operating system, CPU scheduling, memory management, the disk management. The key is disk scheduling. The simplest way of doing it will be what? What do you think? Any management, simplest way of doing scheduling is, so not necessarily system, just resources. The operating system is like a politics, right? Your resource is always limited, and how to do allocation of resource. That's a politics. If there are infinite amount of money, infinite amount of authority positions, then there is no competition, right? Always resources are limited, and we want to strategically allocate to, to the demand in a certain order, right? So that's how to do it. That's really, politics.
Low.
And then operating system is really about the resource management scheduling, right? And the part of the type of resource we are talking about is disk. And for disk demand, there will be read-write requests. I want to read this file. I want to write on this file at the end or in the beginning, things like that. So yeah.
It's this management is done by low priority, high priority.
Disk management is a part of the operating system.
Yeah.
So part of the disk driver, right? So it is in terms of priority. I mean, typically it will be for it's really everything is under CPU. I have to read this one under there's a shared bus, right? So I have to send this to the main memory, or I need to CPU in the reading the instruction. This is a read command from a file system, and then once that is has to be done, then it will be done. There are some interruption priority overriding operations too, but suppose that's not the setting aside that special interrupt, right? In fact, actually, the read-write access is interrupt. So if you keep thinking, oh, wait a minute, I need to go somewhere, disk to read the file. So that's actually from the CPU side, it's an interruption. But given the I/O access, how to do that? That's actually important issue, like any other resource management. And the question, going back, did I answer your question?
I still didn't. My question was, does the disk management goes through like high priority to low priority?
Compared to what other priority?
Like if they want to manage the disk, like you said, it's not infinite, so
Right.
it need to be maintained. How
Right.
much needs to be given? So is there any category like this is the high priority, we will give this amount
So
of this?
when you say different priorities, that means you have something different aspect in mind, right? So we are just talking about the only disk. The other things will be memory access, different I/O access.
Okay.
And all the I/O access decision done by CPU.
CPU. Okay, got it.
So CPU might not need to access disk. It's just busy doing computation, logical operation. But suppose now disk access is the disk access request that has to be done to move forward in the program logic, right? Next line, it's in the assembly code. It is reading a file on certain block, right? So when that happens, again, the question back is that what is the basic way of handling the scheduling?
Labeling tasks.
So label the task are labeled like a depending on somewhere. Really love you can answer, right? If you have, I have 10 apples and a lot of people are coming, and what is the basic strategy? This is a simple, actually, not a trick question. You know this. You guys know this.
First come, first serve.
That's it. Right? First come, first serve, right? That is a really baseline. A lot of research is that how can we do better? Can we do better than that, right? So that's the baseline. We want to do better, but also we can think of the real optimal solution. Oftentimes we don't know what's going to happen in the next second, next minute, but suppose in the evaluation research setting, we know this is a set of the request, then if we have a whole global picture, then I should have satisfied this demand first rather than this, then I could have saved this travel time, right? So that can happen. Research, the scheduling idea will be somewhere in between, hopefully better than first come, first serve, but it will be less than optimal solution. And if we can go closer to the optimal solution, that is really good thing. That's how the research arguments typically is about. So here, what I'm saying is that knowing the hardware is important for us to do better management of the resources, and this case is one of the example, part of the scheduling. HDD has this inevitable part. SSD is different. SSD is the purely electronic one. It's a random access. The more worst example is tape, cassette tape or video tape, VHS. It's really sequential access device. So it does really takes a lot, the
Space.
longer time, and sometimes depending on where the head is, how fast you can reach to a certain spot of the disk, it can vary, right? SSD, you don't have to worry about. That's just another category of saying the disk types is that whether it's a random access device or sequential access device. LP, you may have seen that, that's all the sequential access device. By the way, going back, so about the disk, HDD disk, the typical measurement parameter, performance parameter is the total number of bytes transferred over time, right? So how many bytes can be read or written and transferred. So that's the typical measurement parameter, and the access time relates to the mechanical movement of the read-write head. Our goal will be, or scheduler's goal will be minimizing such mechanical seek time. It's basically how physically how far the read-write head to travel in and out to be able to locate and do reading and writing. So there has been a lot of discussion in algorithms. Operating system, again, our prerequisite course, it really is about the resource management, CPU, memory, storage. In the storage part, you have learned about file system and also disk scheduling too. So disk scheduling, first come first serve is of course one of the scheduling algorithms, and there has been a lot of scheduling algorithms that has been proposed. You can take a look at that. And here's an example. When there is a request in a certain the sector of the cylinder in this order, like 176, 79, 34, 60, 92, 11. This is the order because this is the order coming from the application, running application processes. So, and then suppose the head is at a certain location, and depending on the scheduling algorithm, it might continue to move on the same direction. So suppose there will be some direction is there, then the OS. This is an OS course quiz question or exam question. How much time do you take or how much distance for a read-write head it has to travel to meet all of these requests. So again, first come first serve, we'll be going back and forth following this sequence. This is what do you think? What is this? Shortest seek time first. Yes. So this is a really theoretical optimal. Knowing all of these big sequence, typically you don't see what's happening in ahead. I suppose to be able to tell, you know everything. Then what is the shortest seek time first? These are the two extreme case of the performance you can imagine, and these are the other scheduling algorithms that has been proposed before. Scan is just like a scanning. You keep going to one direction, one direction until the end. Suppose there are some requests over there. I'm the read-write head. I don't see at the moment if any demand over there, but still I keep going till the end. There might be some requests over here, but if so, I meet the request and then go back. Okay. So that's a scan. C scan is C for circle. Yeah. So when the paper head is at the end, around over here, this request comes, I can meet it, and then I go back and I can meet the request. So the ones on the end, if the read-write request at the end can be satisfied either very quickly or very late, because I just maybe there was request right after I left, but this one has to wait until this read-write head come back, right? So the performance can be not balanced, uneven, unfair. So for that, C-scan is that logically consider this one and that one connected. So after the head goes all the way till the end, I don't satisfy anything on the way, go back to this beginning, logically connected, and then meet the demand. So the parameter is how to serve a lot of read-write requests as much as possible. That's one parameter. The other parameter can be fairness. So for that purpose, C-scan has introduced. What do you think? Look. So scan and C-scan, it goes till the end, right? Look is look ahead. So if I met some read-write requests in this direction, and then there's another demand over here. At the moment, I don't have any demand over here. Okay, go back. So that's a look. C look, again, it's C for circular. So from here, go all the way back to the other side of the request, and then serve, right? So it really, which one is the best? It depends on the application need. So this is a very good question. What Google has done, what data center, what cloud provider has done is that they look at their demand and the workload, and then based on that they come up with the architecture services. So knowing what's happening is really, really important. Workload. Anyway, this used to be a big portion of the class before. This time I'm not really explaining in detail in a slide. You can, if you are interested, you can take a look. Yeah, but otherwise, I will not particularly test on that. But at least I want you to know these are names of disk HDD disk scheduling algorithms. Okay, that I want you to know. And I think it's after I explained, it's hopefully you can remember. Any different hardware, you want to know what the characteristics of the hardware is. So SSD, the number is also keep changing. It's evolving, and there are 3D storage technologies are also being emerged. For now, SSD, the most dominant one. The characteristics, these are some characteristics that matters for software folks, for system software people. Knowing this really helps not only how to do software better, but as a user, which one to use, right? And which option to select. That's helpful. So what do you see over here? Read, write, and there's an erase. There's a special thing for SSD. For HDD, the demands are either read or write, but SSD, erase has to be done before writing. An erase unit is typically bigger than writing. So I'm reading one block. block is the read-write access unit for this, for computer systems. Block is a smaller than file. So your file can be arbitrary size, say 10 meg, even 100 meg, right? Megabytes. The block size is decided by the operating system. Operating system, it may have a default. You might be able to change it. You can change it if you want. And that's what's the typical block size, by the way, for an operating system to read the portion of the file. Operating system doesn't read a file by bit. Greater than byte by byte. Okay, so it's a block which is greater than 1 byte. Typically, what do you think? It will be less or greater than file size? Less, of course. I said less, right? And the size, give me a guess. 64 KB. Yeah, the K 4K 16 64 32 K byte. That's a typical block size. Okay, so that's a reading, writing, given an operating system or given a driver setting, it is decided. And then erase unit will be bigger than that, maybe 4 blocks. Right. So the SSD first, the unique characteristic is that erase has to be done, and there is an asymmetry. I actually should ask a question. What do you see here? Reading, writing for HDD, it is really about the movement when you read or write. It's the time between reading and write, they wouldn't make much, but I mean there is no difference. For SSD, there is a big difference due to hardware, the way it works. So for software folks, we don't really go into detail much, but at least to know that there is the asymmetry. Reading takes almost 10 times faster. In other words, writing takes almost 10 times slower. So erase doesn't happen all the time. You might erase it in advance. The erase has to be done first. The new write, so once this is erase unit is erased, writing can be done without doing another erase. And then another thing is that there has been lifetime, how many times you can read or write. The HDD is also, every mechanical thing can worn out, but practically unlimited. SSD, how many times the reading, writing can be done. There has been limited. Knowing all this hardware, Samsung, the Hitachi, lots of storage companies that have done, patents, special strategies to make the lifetime of SSD is almost, you don't worry about it these days. I mean, when those first introduced, even as a user, you be careful. Maybe most of people who doesn't know, people not, but some people who knows that the characteristic will be careful so that you don't do writing little by little, things like that. But now with all the algorithms, strategies introduced, it's a less of an issue. SSD is becoming now even more cheaper, but a lot of data is actually already stored in HDD. The event slowly is being transitioned to SSD. Most of the user instances, VM, those will have an SSD these days. DigitalOcean instances was a SSD only. But again, even AWS, they have a Glacier or cold storage services. Then they would lower the storage systems that is lower in the pyramid. We can assume the SSD only clusters, at least within a cluster. So within the data center components, we talked about the servers and then different storage, the technology hardware types and characteristics of those. Now we are not going to go much detail in the networking, but still some of the words I want to introduce in the beginning at a high level. It's not networking yet, and let me go back. So just still we are in a storage, but you can easily imagine that one HDD, one SSD, the product that comes that you can purchase, it has limited in capacity, and for bigger capacity and also for cluster computing or cloud computing that involves lots of data transfer and storage, storing data. You can easily imagine it needs to be networked, right? And there are different protocols, different ways of connecting storage units together. So these are the examples: DAS, SAN, and NAS. What are the letters that you see everywhere?
NAS.
What is the character? S is everywhere, right?
Storage.
System, storage, and also A is everywhere, right? A, but it's access. This is an area. This is attached. A is in all three acronyms, and that means all different things. DAS is a direct access system. In fact, this is not a real, networked storage outside of the server. The desktop, up until recently, students, most of the computer science students, they before you have laptops. Laptops actually, you don't upgrade it on your own much. Is there anyone who have upgraded your laptop on your own? Yeah. What did you upgrade?
RAM.
Memory, or other example can be storage.
Storage also.
So you purchase the component, you open the closure and add it more. When it typically has a limit, it has to have a slot. Motherboard has a slot to add those, right? So if you are adding more storage, that's a direct access system. Like Windows, there's a C, D, and then you add another one, make it each individual the disk as a separate volume, then it will be logical storage volume. Then that's one way to increase the storage capacity, but it's not really networked going over multiple systems. SAN is a network. NAS is a network. NAS network to storage. Excuse me. So SAN is a storage area network. It stands for. NAS stands for network attached to storage. Is there anyone who has a NAS at home who have used NAS? NAS is how about SAN? SAN probably, do I have another slide? Yeah. So later we are going to talk about it in more detail, but here, SAN is the storage area network connected typically over LAN, like a cluster computing. SAN is the one often used for high performance cluster computing environment. If you go to national labs or even industry labs that does the high volume of data sharing and processing, then it can be over SAN. The SAN products are pretty expensive, meaning at least tens of or hundreds of thousands, the several K, 100K level, or even above, depending on, of course, that's the capacity. It uses a special protocol the over fiber channel. NAS, and this is a block storage. I will talk about it again. For now, you just need to know, these are different types of storage, increasing capacity, and what does it stand for. But I thought you might be curious, so just giving a little info. So SAN is over LAN. NAS uses TCP/IP. That means it is over. If it's not LAN, what's the other one? WAN, right? So you can have NAS device at home and access it from school. Not only server but also storage too. Rather than the evolution has been from one big one to many small ones. So that's the evolution. This is some. I don't think I have it on your thing, but like professors, we write a proposal for the HPC, improving HPC for our university, high performance the cluster computing environment. Then we get a quote, we have what kind of research can be enabled. So that's a big portion of the research part. Also, we add that. So this is relatively recently we got a quote from Dell. So these are the price range, just to let you know. So here comes TOR. Okay. So data center architecture. You have seen the real picture. This is the conceptual the picture. Here's a rack. The lots of servers. They have to be connected together. Real form of switch, if you do Google, it really it looks just one new, the rack device that has a lot of ports in the back. But this circular cylinder, this is just a symbolic image that we use in our class to indicate it's a switch. So switch in a rack connects all of the servers in a rack. They also have to be connected together. And typically it's on the top of the rack, because if you put it in, top of the rack, TOR. If you put it in the middle, people have to walk around. You will have an issue. If it's in the bottom, again, you have to step around. You cannot roll a cart around it. So you have seen all the previous pictures of the Google data center cabling at the top, right? All these cabling across the racks are done through the links above a rack. So this is a picture, data center architecture. This is a picture from a paper published from Google. So there will be switches. They have to be, so this is very simple. All of the racks connected by a single switch. Of course, there should be more than one. This is a really simplified version. And for Google scale data centers, it will be, it will be a little more hierarchy. They don't want to make it too much hierarchy, because it can cause further delay. But this is a typical, well, not typical, really Google scale, Google's the connectivity, where there is some hierarchy. What else do you see? What do you see from here?
There is level.
layer,
Layers.
Layers or level.
layer,
Yeah.
and what else?
Looks like a neural net.
Looks like a neural network, right? Yeah. And what else? Boxes, yeah. So these are switching node, but here you see that actually it has a real important meaning, and that's a redundancy. So from any server to anywhere, if something fails, can it go to the different? Is there another route? Yes. So this is actually connecting to all of these groups of these switches. This is for redundancy for the higher bandwidth, and also for availability. We have looked at this Google Data Center tour before. You can also take a look at this one, and also there are many more. So I encourage you to take a look. I actually changed some minor things doesn't show. The next set of the thing that we want to talk about. Do you have a question?
No.
Lovely question. I want you. Anyone, feel free to ask questions. So next set of the thing we want to talk about is the operational issue. So we are still at the overview part. After this, we're gonna look at the compute virtualization, and then network and storage. We might actually change order a little bit this semester, but we are getting into detail, but still at the moment, we are trying to have a big picture, right? So here's a data center, and we want to operate it well. Well, we need to have a metric to evaluate the performance, and these are some of those. The metric that you see is the throughput and latency. In networking internet, in class the quiz I asked, what's the basic at the network fundamental level performance parameters? Latency and bandwidth relating to throughput, and also packet loss. Really we are talking about the packet level and maybe the message level. Here, this is bigger application level, the performance. And when we say latency, there are some details. The time that takes for the running the data, processing data, and running the program, and also transferring delay, and also from user perspective, the per request, and maybe the first arrival of data, like Netflix, how quickly you can start to watch a movie versus well, actually it's a streaming, and there are a lot of technologies. When you start to watch a movie, the whole movie file didn't arrive, right? But you still start to watch the movie, and while you are watching, the later part of the data will arrive. So that's the real first access performance. So I'm talking about the throughput and latency. Within each component, there are different levels. In your technical discussion, suppose you're at a company, here's a performance. You want to ask, these are the class discussions helps you to ask questions, right? The big questions, the right questions you want to be able to ask. In terms of throughput, in the throughput in networking class, it's really about the effective bandwidth, peak bandwidth, the average bandwidth. Those are throughput. From cloud computing perspective, that it's really looking at the higher level user application level performance. The throughput can be how many requests can be satisfied per unit time, how many users can access it at the same time, and also how much data is processed. So when you're in a technical discussion, I want you to be able to say, what do you mean by throughput? Right? What do you mean by latency? And then let them explain in detail. Or if you are offering some services, throughput, and here throughput means blah blah blah. Right? So operational issue. The next thing is that the cost. Right? The TCO is some word that you see often. TCO and CAPEX and OPEX. I believe, how many of you have seen these words before? CAPEX, OPEX, TCO. So maybe not, not many. And as a student in industry, if you go to industry, that probably you might hear it on the first day. How much money? How much does it cost to CAPEX, to the purchase and own that facility, OPEX to run that facility. Okay? So TCO, total cost of ownership, includes two components, CAPEX and OPEX. CAPEX is really about like this, building hardware itself, air conditioning, generator, server, storage, network, all the hardware, things you purchase, procure. These are CAPEX. So if you are doing a business plan, you need money to do all these data center operation, or to run the business, you have to purchase this hardware. That's all part of the CAPEX. OPEX is to run that. So electricity, people, repair costs, network costs, insurance, these are OPEX. Okay? And this is from operator or provider's perspective. From users, if you're a business, just use the cloud. You also have CAPEX and OPEX. So CAPEX is some long-term lease. That's a fixed portion or one-time investment. That's a CAPEX. OPEX is that pay-per-use on these resources, including hardware, services, and even people too. Right? If you, our university later, when we have a DC manager, you want to ask a question to them. So I want you to be curious. If we purchase a big storage unit, we will also purchase the insurance. Suppose something fails and things like that. And also, when something goes wrong, there should be customer service that we also have to pay for that too. So what's the OPEX? That could be some question to ask the OPEX in terms of these things. So this is some operators TCO example. You know that exact number 61, 60. That's less of an issue. But here, what's the biggest component? That's the thing that I want you to know. So server is of course hardware is the biggest one, but energy is a real big one, right? Powering and also cooling too. Hardware is expensive. It's most of the component of the TCO. You can buy cheaper ones, but it also comes with some trade-off, like reliability, competitiveness. If you are the operator, you want to utilize it as much as possible. And again, overview, basic term section we are in. When we say reliability also can be a course. And I taught many modules before, but for now I'm just giving a very high level basic terms about relating to reliability. when you read the articles on the reading list, the papers, they will talk, if it's to do the reliability, like Google file system, you know, they will talk about this. So these are the terms. Failure in time, mean time to failure, mean time to repair, like MTTF, MTTR. How many of you have heard of MTTF or MTTR? No one?
MTTR I heard.
MTTR, yeah. So this is a term that shows the term that is to do with reliability, not MBTI. Four acronym, the four alphabet without any vowel, but still we use it a lot. MTT, F and R. So actually, if you know what it stands for, you understand what it means. Mean time, average time to failure, mean time to repair. Here's the picture. System is up over here, and then it was running correctly. There's a failure. It takes more than, it takes non-zero time to repair. So it takes time to repair, and so this was downtime, and then now it's working, and then failed. So it will go on and on. So this is a time to failure. From here, time to failure, and time to the repair, right? Time to failure, time to repair. In fact, I should say TTF, TTR, and then if you have many values of TTF, you can do an average. That will be MTT, and then same as MTTR. So steady state availability will be, what do you think is the lag time, proportion of lag time over entire time? That is availability. If it's a half of the time all red, then availability will be 50%, right? So the formula is very simple. You add all these together, that will be MTTF plus MTTR, and then MTTF is the uptime, right? So uptime over hold time, that is availability. Let me stop here for today, and let's do a quiz next time. Okay. We often do in-class quiz. Okay.
So today we have a quiz?
No quiz.
Okay.
I hope you're okay. I mean, for those who attended class, dang it, there was no class, no exam, no quiz. But that's a good thing, right?